There you go. Welcome to Nested Loops Session 6. We are doing POODR by Sandy Metz, and we're going to start on the Chapter 6 with Brett.
All right. This is acquiring behavior through inheritance. I guess later on in the book they talk about composition. I feel like anything I ever think or do when it comes to computers, there's people that love it, people that hate it. I guess we're going to love inheritance today. Okay, so I made a bunch of slides. I'm just going to go through them that way. I have trouble keeping track with the book. So there's this section, and each section in the book I've actually included as like the title of each slide. So if you do want to follow along with the book, it shouldn't be that bad. So understanding classical inheritance, and there's a note in the book about how classical inheritance is a play on words for classes, objects that are made with classes. So inheritance is at its core a mechanism for automatic message delegation. It defines a forwarding path for non-understood messages, and the good part is you don't have to write code explicitly to delegate that message. These relationships are defined by creating subclasses. So in order to explain inheritance, we have these examples in the book, and we have this fake company called Fast Feet. Let's assume that Fast Feet leads road bike trips. And road bicycles, if you don't know, are lightweight, curved handlebar, drop bar, skinny tired bikes that are meant for paved roads. I actually don't show figure 6.1 here, so. Mechanics are responsible for keeping bicycles running, and the spare parts that they bring depend on which bicycles they take. So we have this example first shot at this bicycle class that Fast Feet uses, and you see it on the right, and bikes have an overall size, handlebar, tape color, tire size, and chain type. This class works just fine, aside from the fact that 10 speed and 23 are hard-coded as strings directly in the spares method. But we'll see as soon as we want to expand on this or add any other specializations, it starts to become troublesome. And the way that we'll prove that is, imagine Fast Feet begins to lead mountain bike trips. Mountain bikes have beefier tires, straight bars, all that good stuff. And much of the behavior that you need for a mountain bike object already exists. They have a bike size, a chain, and tire size. What's the difference? The main difference is road bikes need a handlebar tape and mountain bikes have a suspension. So let's take our first poor shot at basically having Fast Feet support both road bikes and mountain bikes. It's very tempting. Every single time I read this book, I look back and I go, oh, I've done crap like this a million times. It's tempting to solve this problem by adding code to that class. An example to the right shows altering the existing bicycle class. The new front shock and rear shock variables hold the mountain bike specific parts, and the new style variable determines which type of bike it is, basically. And we see on the right in the spares method, this if statement, which is really just the killer bad part of this. What happens if we want to add a new bike? Later on in the chapter, we see, I think it's pronounced recumbent bike, and we'd have to actually go into this and alter that if statement. And then another problem with it is we default. So there's that whole idea that because we default to a mountain bike in the spares method, you could perhaps misspell the style and not get what you expect, kind of thing. So bicycle has an implied public interface that includes spares, size, and all the individual parts. The size method still works, spares generally works, but the parts method are now unreliable. Because basically, if you have a bicycle, how do you know, first of all, if it's a mountain bike or a road bike, unless the outside code, the code that's holding the object, checks with an if statement or something like that. How do you know if you're going to get a front shock or a rear shock value? Well, if you have a road bike, you're not. So it's impossible to predict for any specific instance of bicycle whether the specific part has been initialized. Blah, blah, blah. Yeah, I said that. Okay. So style, we have this style attribute, and it would have been just as natural to call that type or category, which is really where we introduce inheritance. Variables with these kinds of names are your cue to notice the underlying pattern. Type and category are words perilously similar to those you would use when describing a class. And really, what's the difference between a type or a category? Classes are a type or a category. One way of looking at it, at least. The style variable effectively divides the instance bicycle into two different kinds of things: mountain bikes and road bikes. They share a lot of the same behavior, but as we know, we don't have the rear shock, the front shock, the handlebar issue. Some bicycles, behaviors applied to all, blah, blah, blah. I think we're good on that. Okay, so it goes without saying objects receive messages. No matter how complicated the code, the receiving object ultimately handles any message in one of two ways. It responds directly, or it passes the message onto some other object for a response. Inheritance provides a way to define two objects as having a relationship such that when the first receives the message it does not understand, it automatically forwards or delegates that message to the second. Now, what do I want to say about that? Well, first, does anyone have any questions or any interjections so far? Okay, forgetting what I want to add on that, but I will jump right into some languages have what's called multiple inheritance. And I just want to touch upon that because the book does, which is in Ruby, there's only single inheritance. And in multiple inheritance, you have these situations like when an object with multiple parents receives a message that it does not understand which parent does it send the message. And if both parents implement the message, which one does it send it to? I guess what I was going to say was that the relationship, it always goes upwards to the superclass, so that that relationship. Okay, whether you know it or not, but I assume most programmers on this call know it, we use inheritance already. In Ruby, anytime you create a new class, if you don't define its parent class, you're automatically inheriting from the object class. The fact that unknown messages get delegated to the superclass hierarchy implies that subclasses are everything their superclasses are plus more. I think this is probably the most important, one of the most important parts in this chapter is that subclasses really have to be specializations, and superclasses should always, basically, a superclass should always have stuff in it that the subclass will need. Every string is assumed to contain object's entire public interface. So that's basically what I was touching on, and must respond appropriately to any message defined in that interface. And we have this example, which basically nil is an instance of nil class, and it automatically returns true for the nil method, nil question mark method, and object automatically returns false for the nil method. And because all the objects, sorry, all the classes that we create have a superclass ultimately of object, that explains why nil always returns false. That's one of the most common examples I've ever heard with Ruby. So, okay, UML. I guess we used UML in chapter 4, and in this chapter, we have an example of showing mountain bike as a subclass of bicycle. And this UML diagram on the right basically shows the arrow, the hollow triangle means that the relationship is inheritance. The pointed end of the triangle is attached to the box containing the superclass. You can use UML to describe this. Okay, so basically, we're going to try to break up this bicycle class into two different at least create the subclass for mountain bike. And mountain bike is going to inherit from bicycle, and we're going to kind of write it in not such a great way at first. And so at first we overwrite the initialize method and we overwrite the spares method. And you'll see in initialize we have to call super, but mountain bike, because it's inheriting from bicycle, is still going to include the tape color and stuff like that. We haven't gotten bicycle to be abstract enough. In this code on the right is basically showing that yeah, we're a subclass, we're inheriting from bicycle, but we're not following the rules. Which on the bottom right you can see tape color not applicable. So the UML kind of fake UML diagram. I guess we took a lot of liberties in creating this UML diagram on the right. Shows that bicycle actually contains road bike, and we're inheriting more than just bicycle with the way that we've written it poorly. So bicycle was never intended to be written to be subclassed. And when you slam mountain bike under bicycle, you inherit all this behavior. As written, bicycle should not act as the superclass of mountain bike, but because design is evolutionary, this happens all the time. Hold on. Can someone say something?
Hello.
I apologize. I had wireless headphones that shut off after about 3 minutes of not hearing anything.
It looks like data point lost power.
Oh, okay. Where did they leave off? Like right around here?
What's that? Diego says keep going.
Yeah, okay. So bicycle includes road bike still. Okay, so in the beginning there was one idea of bicycle, and it was modeled as single class bicycle. The original designer chose this generic name for an object that was actually slightly more specialized in the sense that we were creating a road bike. But what's important is the existing bicycle class, just because it's a road bike doesn't mean that we have to call it road bike. Because originally we only had road bikes, naming it bicycle is fine. And Sandy wouldn't want to run you astray in any way and have you believe that you should have created it as a road bike object class. Nor would she, this is said later on, nor would she want you to create the road bike class inheriting from bicycle right off the bat. Forest is frozen for me, so I just want to confirm it's not my internet.
It doesn't look
Okay,
like it.
as long as you can hear me, we're good. Sorry about that. So the original designer chose a generic name, blah, blah, blah. That's about that. Even if one day you suspect that you will have mountain bikes, bicycle is a fine name for the class. Okay, so this is where we actually start to break it up a little bit. Bicycle is a superclass of both mountain bike and road bike. Bicycle will contain the common behavior, and mountain bike and road bike will add the specializations, as we know. Bicycle's public interface should include spares and size, and the interfaces of its subclasses will add their individual parts. Bicycles now in this situation represent the abstract class. We don't want anything in bicycle that wouldn't apply to either one. It's important to note here, and I actually didn't really adhere to this myself so much, but that's why this book is good, is that you'll never expect to create a bicycle object. You'll never call new in this exact scenario on the bicycle. The abstract class is actually never genuinely intended to be created, which of course in college, in Java, with the the syntax abstract. Took about 10 years to understand that. So you think you'd get that. So that's where I go into how some object-oriented programming languages have syntax that allows you to explicitly declare classes as abstract. Java has that. In Ruby, we don't have that. In Ruby, we just trust that you'd know that rule and that's how